Welcome everybody to our final colloquium for this academic year, Duke Physics Colloquium. We have the pleasure of having Professor Kwang-Je Kim from Argonne and the University of Chicago here to tell us today about coherent monochromatic X-rays. And, I'm particularly happy to bring to our awareness the physics that's happening over at the free electron laser lab here at Duke. So I'm very much looking forward to the talk. The rules are the same as always. Professor Kim has indicated that he'd be more than happy to have people interrupt during his talk. If you want to ask a question, you can just speak up. I will also monitor the chat and the raise hand features if you prefer to do it that way. If you want me to be the one who has to butt in, I'll do that. And I'm going to turn it over now to Professor Ying Wu to introduce our speaker.
Thank you, Josh. I hope you can hear me. I'm so glad that we can have Professor Kwang-Je Kim to Duke to give this talk. Kwang-Je is a original thinker, researcher in the accelerator physics and FEL. In fact, he's one of the pioneers of FELs and in synchrotron radiation. Kwang-Je actually was a scientist at Berkeley National Lab for about 20 years. And in 1998, he went to Argonne National Lab. And then he is a Argonne Distinguished Fellow, Senior Scientist, also Professor of Physics at the University of Chicago. He's awarded for his work he is awarded for FEL Prize, U.S. Particle Accelerator School Award, and also the Robert Wilson Prize, which is highest prize in our field. And I actually know Kwang-Je for about 30 years. I still remember when I was probably second year, third year graduate student visiting Berkeley Lab, spending about 6 weeks with the scientists there. The first day I was working, I met Kwang-Je in the trailer. He asked me, well, what are you doing here? And that relationship stuck, and Kwang-Je has been a strong supporter of the Duke FEL program, and of course also our research. In fact, many of his great ideas that were proposed in the 80s were later materialized in our machine at the Duke FEL. Now, Kwang-Je has been a visionary for a new type of coherent X-ray source for now a couple of decades now. So he is really the international known advocate for this new idea and this new direction. So he's here today to tell us about coherent X-ray FEL that he has envisioned and have moved the field towards building in the near future. Kwang-Je?
Thank you very much, Ying. I'm really glad to be here. I was at the Duke campus maybe last time about 10 years ago. And I was really looking forward to be there in person last year, but the unfortunate COVID situation, we had to delay it. But anyhow, I'm really glad to give this talk. Okay, so I will be giving a broad overview of synchrotron radiation FEL area. And toward the end, I'll talk briefly about this new development. But as Professor Sokola was saying, you could interrupt me anytime you need to do so. Okay, so I think all of us know what is synchrotron radiation. It is radiation emitted by relativistic electron when it is accelerated in curved motion. So it's going like this, and it radiation with a small angular divergence 1 over gamma, and gamma being relativistic factor here. So 1 GeV electron has a gamma of 2000, and the angle is 1 over gamma roughly, so it's less than milliradians. So at APS and at the Duke, you have a 1 GeV ring. At APS, we have a 7 GeV ring, which is a major user facility for high energy synchrotron radiation sources. So this is the APS ring. This is Orion Nebula, which there's a blue background, is synchrotron radiations. So at the APS, we are using this light, but not this light. This light is nice to watch. Okay, so rough configuration of a synchrotron radiation facility. We have a storage ring producing high quality electron beam. And as electron is going around here, and tangential to arc, we have beam lines here. And in the beam lines, there are many sophisticated devices conditioning and transporting X-rays. So what is going on here? Roughly, we have electron beam generating X-rays, and you have some optics, monochromatize or focus the X-ray beams to a sample, and then either scattered light or scattered electrons comes out and you detect. And you have various technologies, spectroscopy to determine the energy, scattering to determine the momentum, transfer, imaging to determine the positions. And all of these, you have a unique time structure, which allows time evolution of these various phenomena. So a continuous spectrum, meaning we can tune the energy, high flux, high brightness, and coherence, and this over a broad spectral range from infrared to X-rays allows many experiments, which I think we can say is really essential for 21st century science and technologies. And here are 5 grand challenges. I wouldn't go through these items. Why? Just to say one of the things. Can we design a perfect atom and energy efficient synthesis of revolutionary new forms of matter with tailored properties? So this kind of topic is currently ongoing and is further developing. Okay, synchrotron radiation has developed, advanced quite a bit. X-rays, first of all, was invented by Röntgen before in the late 19th century, and then X-rays has been in scientific use soon after. Especially after this rotating anode was invented, and then the brightness was going up, and it's taken up by synchrotron radiation, mainly originally from the bending magnet, and then device called wiggler, which concentrate the radiation, and undulator, which further concentrate the radiations. And during this whole span, the radiation brightness in some unit went more than 10 orders of magnitude, like 12 or 13 orders of magnitude. So in the early stage of the synchrotron radiation development, this is SSRP, Stanford Synchrotron Radiation Project, built around Spearing in Slack. This was after Spearing has discovered this basic J-psi particles, but then there's one small area which was used for the synchrotron radiation use. And in United States, I think this was the first serious effort to make use of synchrotron radiation. To illustrate what is this high orders of development in the brightness means in terms of science, we can show this, that this famous diffraction picture taken by Rosalind Franklin in 1951. The experiment was done in 1951 through 1953. The paper was published in 1953 together with Watson Crick, the famous double helix the paper. So she took this using this conventional X-ray tube. And it took 50 hours to take this picture, but this was a marvelous picture showing a very clear indication that this was a spiral, double helix. And Watson, Crick, these people analyzed this much more and built a detailed atomic model laying the foundation of the current life science. Now, 50 years later, and more than 50 years later, a few years ago, there was this, not the picture taken, but its analysis using new scattering data, mapping the ribosome in the atomic level. This was experiment done at the APS, and it's a 2009 Nobel Prize. It's really explaining how the ribosome take the DNA data to production of the proteins. So compare the amount of details that we can explore. Okay, so a few properties of the synchrotron radiation. It starts with a bending magnet with a broad bandwidth, spectral bandwidth, perhaps like 10 kilo electron volt. If we use a device called undulator, we can narrow the spectral width, perhaps to 1 electron volt range. Within here contain the 10 to the 8 photons. So it's a big step there. This is Klaus Horbach, who really revolutionized this field of undulator construction by introducing permanent magnet idea. This is a young fellow assisting him. So the basic principle of undulator is as follows. It's a device, simply periodic magnetic device, where magnetic field goes up north-south along the electron trajectory. There is this undulator device, of course, in the Duke FEL laboratory. So suppose an electron emit one radiation front at one point, and then electron travels by, and in the second equivalent place, it emits another radiation front, and this propagates further and further. So the main point of this is that during one undulator period travel, radiation front advance one wavelength. And this wavelength is simply the difference between the distance traveled by the light in the straight path at the same time and the distance, the effective longitudinal distance traveled by electron. So electron is slightly slower because of the gamma factor, and also the fact that it is going a curved trajectory. So that difference gives you this small distance, and you can see that this distance will be proportional to 1 over gamma square. So in the formula, the wavelength of the undulator radiation is related to the wavelengths of the lambdas of u. Lambda of u is undulator radiation period. Here, I forgot to put the lambdas of u here. But basically, this magnet period, which can be few centimeters or a few tens of centimeters, is squeezed by 2 gamma square factor, which can be more than million. And this is the reason why out of a centimeter, you can produce angstrom radiation, which are X-rays. And furthermore, we can readily see that if there's an n sub u period of undulator, the wave train it generates will be n sub u cycles. And if radiation has n sub u cycles, its bandwidth is 1 over n sub u. And the n sub u is typically like 100. So therefore, you can produce bandwidth of 1%, which is very narrow, not entirely monochromatic for some purpose, but we call it pink beam. Okay. So this is many different kind of undulator. It started with electromagnet. Electromagnet is still for certain application very useful, especially if you have to change the parameters, changing polarization properties and so on. And there's electromagnet of par excellence in the Duke FEL facility. As I said, the basic, the revolution came when Klaus Horbach introduced the idea of using permanent magnet so that we can build a shorter period and the strong magnetic field undulators with a permanent magnet. So this is basic design of permanent magnet. And all these are the structure, mechanical structure that has to go with the undulators. Normally, we prefer undulator poles to be on the vertical line so that you can do spectroscopy or something dispersive in the horizontal plane without not much force. Because of that, there's a certain conservation of the force. You have to deal with a very strong vertical force here. So you need a massive mechanical structure to stabilize this structure. So that's why this is so massive. A few years ago, Efim Gluskin and his collaborators at APS came upon this idea that if we put the poles not in vertical arrangement, but in horizontal arrangement, then magnetic force can be quite small. So therefore, you can control this device simply by spring arrangement. And this making undulator much more compact, easily to manageable. And this is currently now being installed as a LCLS2 undulator, which I'll talk about later. Most recently, there's a development of the superconducting undulators. So we all know superconducting magnet is much more strong than electromagnet. But because we have to also have a short period, in very, very short period, superconducting doesn't really help. But if we go to reasonable length, like here is a 15 millimeter, 1.5 millimeter, in this region, superconducting undulators clearly wins. The superconducting undulators was first, historically, the first introduced by Orsay at France 50 years ago, one of the first devices. But the technology that goes with the superconducting undulator, matching the expansion coefficient and all those, you have to cool down, cool up, and so on. So that never materialized. And then the permanent magnet undulators are much better. But 50 years later, the technology has improved very much. And we are in APS now, there's several superconducting undulator based upon titanium, niobium titanium, the magnet. And now this niobium tin device is also being developed with a very high performance. The only problem of niobium tin is that this coil is very difficult to deal with mechanically, but that problem is being solved. One of the prototype device is under construction right now. Okay, so want to sit back a little bit, going on the coherence properties of the wave. And coherence means ability for interference. So for example, if we consider one wave train, say single electron emit a train of wave, this is a quite coherent. Temporally, the bandwidth, as I said before, of this, if there's a n sub u period, then bandwidth is 1 over n sub u. Now, if we make product of the bandwidth and the length, this is a phase space area. So in the okay, this is the transverse. So this phase space area, two-dimensional volume, becomes lambda. And exactly the same thing happens for the transverse. If we confine radiation in certain transverse dimension delta of x, it will diffract by delta phi diffraction angle being lambda of delta x. So here, this equation is exactly the same equation. Delta omega of omega replaced by delta phi, delta x replaced by the size delta t. So the product of delta x, delta phi is again lambda in the transverse space. So in this case, we have coherent case and this phase space area in respective cases about lambda, and it will exhibit interference pattern. If we do a little bit more rigorous math, then we can find out what is the field profile, which gives you minimum product of a sigma r prime. And you find this is wavelength divided over 4 pi. And this is nothing but Heisenberg uncertainty, Heisenberg minimum uncertainty product. And this Gaussian field profile is also the wave function which give a minimum uncertainty product. But of course, this is this particular case, we can also call this is Fourier product, because this all comes out from Fourier transform. You have a profile, field profile in the X, you make Fourier transform to find out what is the angular profile and the product, and you have the minimum product if you have Gaussian profile. Now, if we have radiation from beam, such as from undulators in electron storage ring, electron beam has, so these black dots are electron beam, and electron beam, each electron emit radiation in each propagation direction and located in the transverse position of the electrons. In the phase space, this blue background is electrons, electron distribution, and each discrete electron emit undulator radiation like this. So the total phase space is a convolution of radiation phase space of individual radiation and the electron beam distribution. Exactly the same thing happened in temporal dimension also. We are going in these directions, and each electron emit radiation packet. And if there's many electrons, we superpose them, and the overall result is this superposed pattern. And naively, you might think that if we have 1 million or 100 million electrons, and each emit like this, the result will be quite complicated. But actually, that's not so, because there is definitely some coherence by single electron. So the overall pattern is each given a coherence length. So if electron length is 10 times coherence length, there will be about 10 coherent mode here. Okay. The only thing is that this amplitude of radiation is not number of the electron times each single strength, but it's the square root of n, because it's incoherent superposition. So radiation strength is not n sub e square. So that's I have written over here. The important point is that combined phase space of electron together with the radiation beam is a convolution like this. And generally, this is greater than lambda over 4 pi, which is a minimum phase space area. If this is too much large, then the interference pattern, the visibility will vanish, and there's no interference. But if it's close to lambda over 4 pi, the radiation interference is quite pronounced. The brightness that I showed you before is really defined by number of the photons emitted divided by the phase space area, 2 transverse dimension and 1 temporal dimension. And so this will be brighter if you can reduce the phase space area, and the number of the photon is proportional to the number of the electron. So if you have a more intense beam in smaller phase space area, in smaller emittance, then you have a bright beams. Okay, so we should talk about briefly how we can make this electron beam emittance small. And the idea of doing that was invented in 1975 by this Brookhaven accelerator physicist René Chessman and Ken Green. Ken Green was really a pioneer in this field. And the idea is that electron beam emittance in storage ring is excited because of the radiation process in bending magnet. So if electron comes, and if we radiate 1 photon before entering a bending magnet or during the bending magnet too, its energy changes a little bit, and that gives you slightly different trajectory, displaced by transverse directions. And this difference excites the emittance. So it is necessary, and the idea of Ken Green and René Chessman was less confine the area in the storage ring where this happens. And so they so-called divide the bending magnet, split the bending magnet and put quadruples in there, so that this thing happens only within here. if you do not do this special design, if electron trajectory once is altered here, it keeps altering and propagate all the rest of the storage. And by using these device, that excitation is limited to here. So the so-called third generation storage ring employed double band achromat or triple band achromat. This is number of the achromat per bending unit. So this particular example is a double band achromat. So it is obvious immediately that if per bending magnet, if you increase this achromat, clearly the emittance will become better. So that was actually seriously proposed after some 10 or to 20 years ago. And this is making, rather than double, triple, and here particular example is a 7-band. And 7-band is currently the most number of the band used. So although this idea is simple, actually implementing this is technically quite challenging, because you need you need to make everything very small, fit it into the tight space with all tolerance and so on. So this was really the technology innovations, and this first was implemented by Swedish, and then afterward several light source, including APS, is undergoing this upgrade. And so in this is APS ring. So this is before the upgrade, and the beams spot after upgrade will look like this. And corresponding to this, the radiation emittance goes from here to there. It's more than 2 orders of magnitude improvement. So APS is currently in the third phase of implementing this. Will be shutting down storage ring operations, I think in the middle of next year for 6 months in order to make this changeover. Okay, so that was how am I doing in time?
You're doing just fine.
Okay.
20 minutes or more.
Okay. Okay, so now I would like to go into the next idea, to the free electron laser. So in order to explain that, I have to explain, we discussed the temporal coherence a little bit more. So as I said, if we have a single wave train, this has a bandwidth of 1/n, and the product bandwidth length product is simply lambda. And this is coherent, and this can interference pattern. If we have many wave trains due to many electrons, as long as there's a long region of periodic region T, if this is much longer than at the end, so at the end, this starting point of these wave trains are slightly different, spread over delta T. As long as this is delta T is much smaller than this region, then this will be more or less applied. So this is still coherent, meaning it can do an interference pattern. If we sum over these waves, we obtain the resultant wave will be something like this, and with the amplitude of here, square root of n sub e. But it is still coherent. Now let's see what I have here. What will happen if we put all this starting point exactly the same, then all the waves are in exactly same phase. So therefore, the amplitude add. So if individual amplitude is 1, if we add up n sub e amplitude, then the amplitude is n sub e. So then radiation intensity is a number of electrons squared. So although the interference pattern is basically the same here and over here, in this case, we have enormously enhanced radiation. So this is what is happening in FEL. Okay. So FEL was invented by John Mady. He died in 2016, unfortunately. But he came upon this idea when he was in graduate school. And the idea is basically this. So if we have an undulator and a wave is coming in, and this green dot is an electron, and look at the motion of the green dot and the wave. So the point of this is this. A particular electron located here, after going every period, because of the periodicity of the wave, this electron sees the same environment, the same radiation environment. It sees the same phase of the radiation. So therefore, the interaction between this electron and wave keep accumulating, namely it's resonant. So this electron, it keeps increasing the energy. Electron halfway between them will keep losing the energy. So therefore, if there's an electron beam here, electron beam will develop energy modulation, and that modulation is with the periodicity of the wave. So if energy is modulated, then after some time, this energy modulation translated to the density modulation. And the electron beam modulated with density of the periodicity of the radiation will emit coherently. So therefore, instant radiation will be amplified. So that's the gain mechanism in free electron laser. I was going to show the simulated development of electron into the bunches, but I don't think that the movie works here. But so the simplest implementation of this free electron laser idea, free electron laser was verified in infrared and visible and so on. And Duke FEL has recently achieved, I heard the record, a short wavelength record in the VUV range. But people realized already a long time ago in 1980s that the real application revolution will occur if we can make FEL for the X-ray. But in 1980s, when this was proposed, we didn't have electron beam technology and so on. But it had to wait 20 years. There was roughly 10 years of theory development, another 10 years of trying to get the project off ground. And finally, in LCLS, using Cu-linacs in 2009, this was achieved in LCLS. So the main difficulty of making X-ray FEL is that in order X-ray FEL is that normal FEL is in the resonator, and the resonator requires optical cavity, and optical cavity requires mirror. Now in X-ray, there's no mirror which reflects 90 degrees or at least in large angle. And but at the same time as Claudio Pellegrini and his colleagues proposed using single pass FEL. So this is not really FEL oscillator, but very high gain amplifier. Let's go back. And in the high gain amplifier, you start with the noise, and you make the undulator very long. Then there is a gain process occurring, and the gain from here to there is perhaps like 1 million factor. So initially, very noisy spectrum gets amplified and become a quasi-coherent radiation afterward. So this radiation transversely become quite coherent. Initially quite incoherent, but quite coherent. But in temporally, it's a chaotic light. It has a coherent region, but stochastically summed over, right? But this X-ray intense quasi-coherent radiation first constructed by LCLS in 2009, and several others since then. And the LCLS2 will be planned to in 2020. I don't think it's really, but they are going to complete it around the 25 by with a superconducting the Linac. So this will be a major user device. So after constructing the basic SASE devices, LCLS, there's been several improvements. One is so-called self-seeding, which is you put the first monochromator, and then you further amplify monochromator, so thereby reducing the spectrum from 20 electron volt to half electron volt. There's a factor of 5 improvement in the spectral brightness. So in the high gain device, these are all naturally very short pulse device, because in order to make high gain, you need to make high current. And the easiest way of making high current, of course, is just compressing the bunch. So in the SLAC, electron bunches are typically 20, 30 femtosecond long. It's quite small. So the peak current is a few kiloamp. And people is not satisfied with 20 femtosecond. They want a sub-femtosecond pulse. And that has been recently achieved at SLAC, and using this idea called the eSASI, which you have, you first produce an infrared radiation, and using this infrared radiation, you modulate electron beam like this. And you use this portion, which has enhanced current and much shorter period, the length. And using this, you now generate the main radiation. So in this way, you can produce sub-femtosecond, they call attosecond X-rays. And this is receiving quite an attention recently. And they have a project going into LCLS2 with a superconducting device. Okay, so parallel to FEL amplifier, at the same time, the FEL amplifier in X-ray was proposed. There was actually a proposal to build the X-ray oscillator. And so, as I mentioned, the main hurdle there is to build the optical cavity. and you can build optical cavity if you use Bragg scattering, for example, using the diamond. So that idea was proposed about the same time as high gain FEL was proposed. But at that time, once again, we didn't have a quite reliable theory of this FEL device. We didn't have the accelerator producing shootable beams. But in the meanwhile, this was improved, and we have revived the idea of XFEL oscillator in 2007. About at the same time, actually slightly before, the SLAC group has proposed X-ray regenerative amplifier. This is basically the same as a FEL oscillator, but it is high gain in the past. So therefore, it doesn't have a very narrow bandwidth as an XFEL oscillator, but it has a very high gain. So its requirement on the mirror is less stringent, and the bandwidth it produces is a little bit more large. But on the other hand, the radiation is more intense. So together, oscillator and regenerative amplifier we call a cavity-based XFEL. The performance of the cavity-based XFEL is over here. This is oscillator and this is XFEL. And compared to the diffraction limited storage ring, the APS-2 type, is by going to LCLS2 high gain, we have already like 4 orders of magnitude of improvement. XFELO, XFEL will give another 2 to 3 orders of magnitude improvement in the brightness. And in the XFELO, basically it's due to this very narrow gain, that's big. And XFEL, reasonably narrow gain with a high intensity. Okay, there's a new science, several new science you can talk about. The one, to me, the most easiest thing to understand was the application to the Moessbauer spectroscopy for medicine and nuclear nonlinear optics. So this example is studying the role or how the red cell operate in a cell. And this is very important for medicine. If red cell, of course, bring the oxygen, and the transport of the red cells through shell should be just right. If it's too much, it is poisonous. If it's too less, it doesn't provide enough oxygen. And the studying this red cell transfer is looking at this red cell has many ion atom. An ion atom has a very narrow nuclear resonance in 14.4 kilovolt. And XFELO has, because it has very high spectral bandwidth, narrow bandwidth, the resonant width of nuclear resonance is a nano electron volt, very, very narrow. Synchrotron radiation has a 100 electron volt, but the XFELO has a milli electron volt, so it's the highest spectral resonance. So the mapping out the red cell interaction with the cell that kind of study is currently going on in the storage ring FEL, the storage ring sources, taking about 1 week to record this process. If we use XFELO, this will take a few minutes, maybe less. So you see the enormous applications. this is if we have achieved XFELO, then we can really think about stabilizing the position of these Bragg crystals really tight. So control the distance, round trip distance within a fraction of the wavelengths, which is very tight requirement. But certainly compared to the LIGO, this is very easy. If we can do that, then now we can form a Fabry-Perot resonance. That means we are generating X-ray spectral comb. You heard about spectral comb using conventional laser techniques. And with using, if we can indeed do spectral comb of a nuclear resonance, then we can do all this quantum optics currently doing is atomic physics. We can do that quantum optics with nuclear physics, with many applications. Okay, so I have now just a couple of paragraphs left. So at Argonne and SLAC, we have been doing independent research. At Argonne, focused on the XFELO oscillator theory and simulation, and diamond optics. In particular, we have to make sure that the diamond, this very high reflectivity diamond, survive in this intense X-ray environment in the optical cavity. And actually, we have demonstrated that using high quality diamond from Russia. I think it is in the next slide. In the SLAC, they have been developing XFEL theory and simulation, and also trying to develop the Q switching. In XFEL, after a few passes, you have to kick the radiation out. So they were talking about Q switching, but Q switching is maybe too difficult. They are making the crystal. They're making the radiation spilling out of the crystal. It is a most recent result. But anyhow, we said the really testing this cavity-based XFEL requires superconducting Linac, because this device needs a constant bunch. But however, it occurs that even if you do not have a constant stream of the bunch, as for the simple test, we can simply use two double bunch. So we use a copper Linac over the Stanford, rather than each time it produce single bunch, let it produce a double bunch. So you have RF wave generating for one electron, and you produce electrons in different RF bucket, and the time separation is a one round trip. So if you can produce this bunch pairs, let the first bunch radiate and make the second bunch amplify. So you can observe the gain in the optical cavity, and then also you observe the ring down in the cavity afterward, and which will give you indication of the cavity qualities. So that's a very serious experimental effort, and if successful, will give quite a credibility to this CB XFEL cavity. So let me see. Okay, so this was the Argonne test of the crystal. We have this crystal, high quality crystal, using APS beamline, we have tightly focused the beam so that radiation exposure density at the spot is similar to what we expect in XFELO. It's roughly 12 kilowatt per millimeter square. And we exposed 4 hours. One in the high vacuum at 10 to the minus 8 torr. One is normal vacuum, poor vacuum, 10 to the minus 6. If its vacuum is poor, then we see this carbon deposit, which is normally observed in all synchrotron radiation sources. With a high vacuum for 4 hours, there was apparently nothing happening in the eye. If we look at this diffraction properties, actually these two spots are not that much different. That means all this scattering, the deflection effect is effect in the body, not on the surface. And this can further be removed by annealing and so on. So this is at least the indication that diamond will survive. And also high reflectivity and so another property is that if we cool the diamond to the cryogenic temperature, then thermal diffusivity and thermal expansion coefficient, thermal diffusivity becomes very high, which means that the heat spot just disappear soon, and even if there's heat, expansion coefficient is very small. So therefore, the thermal effect can be minimal. Okay, so we have started this experiment 1.5 years ago from with funding from DOE. So we have a 7 segment of a slug LCLS undulator. This is LCLS 2 undulators, still not using because LCLS 2 beams are electron beams are still not there. But we use a 7 undulator. Then we have this chicane. We produce double bunch. The first bunch goes along, produce spontaneous emission, and when this comes here, then the second bunch produce a second X-rays, and then see the amplification here.
Couple more minutes, Professor Kim.
Okay, I'm almost done actually. So this is a LCLS 2 undulator hall. This is the 7 undulator unit, and this is actual site there. And we even did a very important high precision experiment, verifying that the space from here to the wall is enough to accommodate these other gadgets here. Okay, actually that was my last graph. So thank you very much.
Thank you. We have a chance for questions now. As is our practice, we open the floor first for questions from graduate students, postdocs, undergraduate students. Would anybody like to ask a question? Perhaps then we'll open the floor to anybody who wants to ask.
I'm going to ask a question.
Hey.
Kwang-Je, you have shown a lot of activities at Argonne and SCRF. Are there other activities around the world in the Europe and Asia?
In the Asia, I know very little, but I know that Haxiao Deng's group in Shanghai, they are certainly building superconducting undulator based X-ray FEL, and they are interested in oscillator option. There's also effort going on in European XFEL, and so they have a space and a plan to put undulator in one of the hole there, and their configuration is a back-to-back scattering configuration. So a little bit simpler optical configuration, but on the other hand, their electron beam is not the pair bunch, but they have a constant stream of electron beam coming. So they are actually quite, if they are successful, it means they have demonstrated full XFELO. Yeah, so.
Ken Long?
Hi, Dr. Kim. Thank you for the nice talk. I have a question based on, as you guys move towards the sub-picosecond pulses, you start running into space charge effects at some stage, and and when does that start coming into play? And also with your magnetic fields, when I've built kind of Halbach arrays in the past, we've had surface field fluctuations on the order of a couple of % from the manufacturing, and you're putting yours under very high forces. So what kind of mechanical and magnetic field tolerances do you need in building these undulators?
So the first question was about space charge when compressing bunch to short pulse.
Yeah,
yeah. Right. So there are certainly space charge effect, especially in the very beginning when the electron beam energy is small. So associated with that, there's electron beam instability developing, so-called micro-bunching instability and so on. And so because of that, so both FEL and this instability develop if electron beam qualities are very good. So some people call it FEL as an FEL instability, which I don't like. FEL is a coherent process, but this microwave instability is a certain instability, and they cure this by messing up electron beam quality intentionally. So what they do is that they put this small FEL section over there. They put a laser and FEL, laser and undulator, and let electron beam interact, so that their energy spread becomes larger than what is originally produced. So by doing that, they control this microbunch instability, and so by messing up the quality, you make the FEL quality better. So in the Chinese language, it's called you attack disease by poison. And your second question was about undulator, I think. How precise you can control the magnetic field quality and so on and so forth. So those are detailed the technical questions, and one of the ways that you do all this step of the recording, you measure each pole magnetic field carefully, and you shuffle them in order to compensate for a gross misadjustment. And there are many detailed steps which I'm certainly not expert of. And this idea about the superconducting undulator has been tried. I said at the beginning in Orsay, in the 1950s, no, 1970s, that failed miserably. And about 20 years later, it was again attempted at Brookhaven laboratory. So they built, they thought much better mechanical structures, and they tested it out. And in the process of cooling down and heating up again, the structure just simply warped all the way. So it was not useful. So it is a extremely careful engineering step. And I'm all the time very amazed that these engineering engineers can deal with these properties. You know, the XFEL optical cavity requirement, you have to have these diamond crystal stages. The angular tolerance is tens of nanoradians. But there are excellent engineers who can deal with those things.
Calvin?
Yeah.
Calvin?
Yeah, thank you very much. So I'm a nuclear physicist. Thank you very much for a very interesting talk, Dr. Kim.
Yeah.
So my question is a practical one about mechanical tolerance.
Mm-hmm.
I work with Ying Wu, but I guess I don't talk too much about the precision of the mechanical tolerance of undulators. But your talk stimulated this question, and what are the kind of mechanical tolerances for these undulators that make X-rays? Are they sub 100 micron type mechanical alignments, or even smaller? And what about the uniformity of the field in the oscillating poles?
The mechanical tolerance and magnetic field tolerance in the undulator, I think it's a few micron range, and this is achieved in current X-ray FEL at SLAG and Europe, and they also have this feedback mechanism. You look at the electron trajectory and correct this magnetic placement. That's the reason why, for example, there's all this. Let me show you here. So the most recent example, do you see this? There's a lower here. So okay, in these devices, if poles are arranged in the vertical plane, the magnetic force attracting or repelling this is huge. So therefore, you need this massive mechanical structure to stabilize it. And in addition to that, you have to fine control this motion. In here, you put the poles in horizontal plane. So therefore, the force is the horizontal force that is much more easy to deal with. So they use the simple spring mechanism. What I'm saying is that I'm really not answering your question in quantitative manner, but it is this tolerance in magnet I'm least concerned with. These are all solved, and the future devices, oscillator or CVXFEL, that tolerance is not any higher than what is currently achieved there.
So may I ask another question?
Sure.
Can we interpret these undulators to be zero effect on the beam emittance, and you can make them infinitely long?
Certainly, you need to be careful if you want to make infinitely long. but in Japan, they have this 20-meter undulator, which is pretty long, and you put the undulator in the correct place where the so-called dispersion is 0. The dispersion is the place where I indicated this. If you emit photons, then electron trajectory becomes transversely translated, and the angle is also wrong. And normally you design the place where you put the undulator so that this dispersion is 0. So then the effect on the beam is minimal. Now you can also design so that you can put the undulators or wiggler in the place where you the existence of this insertion device can cool the beam. And if you are wrong, you can also heat up the beam. So there's several such schemes, but it's all you can deal with it.
Thank you very much.
Let's get a couple more quick questions. Junyan.
Hi, Professor Kim. So thank you for introducing so many interesting FEI ideas. So I have a question about the idea of the stabilized XFELO to do the mode locking, like to the frequency count. So to do this, you need to have a cavity length control at a level of a few radiation wavelength, right? So for hard X-ray, 3%, yeah. So then for hard X-ray, we are looking at like a few picometers. So how can you realize such a this control, length control with such a accuracy, precision?
Yeah. So my first answer is LIGO achieves a distance control of 1/100th of proton radius. So this is much relaxed from that point of view. Here, you will need some feedback. So for example, one kind of feedback you can do is that you couple this to the nuclear resonance again. Do you see this? Do you see this, the view graph here?
Yes.
Yeah. So you have a nuclear resonance, and you use ion 57 14.4 resonance, 14.4 kilovolt resonance, which is a bandwidth of a few nano electron volt. Basically you try to so the comb line is shown over here, and you try to lock in to one of the comb line, and as soon as you catch the motion, then you will need a piezo feedback.
I see. So essentially, like for conventional lasers, you lock the cavity to a second cavity, but in this case, you are locking it to resonance, to a nuclear resonance, right?
Yes.
Oh, okay, that's interesting. Okay, thank you.
Yeah.
And last question from Mark Imamian. You're muted, Mark. You need to unmute.
Thanks, Professor Kim, for this wonderful presentation. I had two questions. One was asked by Professor Howell. Second one was, you mentioned double mode or double bunch.
Yes.
Technique. Is that the same as the master oscillator, the power amplifier, like what we used to call MOPA?
Yeah, but not as sophisticated. The master oscillator amplifier is 2 FELs.
Yeah, that's right.
2 lasers. Here, we are just trying to demonstrate the first gain. So we are just using 2 electron bunch because in US we do not yet have any superconducting LINAC available to do this experiment. So the easiest way is to use the copper LINAC as slug. And copper LINAC as slug, the problem is that it produces bunches in 100 hertz, which is, so we cannot do any amplifier experiment. But we can, in single bunch productions, we can put 2 electron bunches in that single RF cycle. And so the RF cycle is sufficiently long so that 2 bunches can be separated by, in this particular case, we are using 6.5 meter, which correspond to 624 RF period. And they are there. So if we do that, then the first bunch simply produce a spontaneous emission, and we catch the spontaneous emission, and that goes around. And when it comes here, then it hits, it gets another radiation from the second bunch. Then it meets the electron bunch, second electron bunch. And then there's a single pass FEL gain, and we want to measure that. So this is very, very first step measurement. But in lieu of in doing that, we will have demonstrated that X-ray cavity actually work with the tolerance, and we should get a reasonable agreement of the theory with this experiment. The interesting thing about this optical cavity, this X-ray cavity is exactly like accelerator physics cavity. So if there's some certain crystal misalignment and electron beam comes not on axis, then the radiation produced by it will perform betatron oscillation going around. And so if the betatron amplitude will signify the misalignment.
So I don't want to cut off this discussion, but I want to sort of formally end the colloquium session. Professor Kim can hang on for a little while, and people who want to keep pursuing these questions are more than welcome to stay online.
All right.
But, I want others to feel that it's fine to leave now if you need to. So thanks again very much for the colloquium, and yeah, we're ready for additional discussion for anybody who wants to stay.
Yeah. So one more question if I have.
Okay.
Yeah. Calvin, do you have another question?
Go ahead, Yang. I had one more question, but if you want to ask a question, go ahead, Anal.
No, I'm leaving. I was just giving the final applaud on my way out. Thank you very much.
Thank you. Yeah.
Thanks, Josh. I'll stay on. Yeah.
Yeah.
Mark?
I did want to ask one question, sort of, well, one very trivial question, and then one sort of general question. So the trivial question is, what's the difference between a wiggler and an undulator? You had them both on your slide, and you made it sound like an undulator is a major development beyond a wiggler. Is it really just the same idea, but built to better tolerance?
So I can say wiggler is like a Texan cowboy, and the undulator is refined Parisian champagne or something. In undulator, as it suggests, the oscillation is much gentler. The reason why you need what is good with a gentle oscillation is that the radiation from one period can interfere with second period. The wiggler, the original idea is simply to control the radiation fan So if in the bending magnet, it will be like the raindrops spreading in the umbrella. It goes in the tangent direction, and in principle it go all the way around the 2 pi, right? In the horizontal direction.
Mm-hmm.
Did you get what I'm saying? So
I'm not sure I'm not really fully getting it.
So in the bending magnet, you say the electron beam is bent at an angle of delta theta.
Right.
And delta theta can be 10 milliradian, 20 milliradian, or 100 milliradian. Normally, I guess more than 100 milliradian. Then radiation will be angular spread horizontally will be 100 milliradian. Because it goes along the tangent. And regular, you want to get the smaller angular spread. The simplest way is to use a bending in one direction, maybe the 10 milliradian in one direction, and then next you have opposite pole bending in the other direction. But then all this from all these poles, the radiation will be 10 milliradian superposed each other. So therefore, you control that angular phase. But these radiations are added incoherently.
I see.
Because it's too much bending and there's a lot of phase went on between.
I see. So in the undulator,
the phase advance from one to the next is much smaller.
I see.
So it's in controlled way.
And my second question was a more general question. It would seem I'm probably missing some key features, but it would seem that all these alignments and particularly when you're using scattering from diamond crystals to direct the beams, that the question is, can you vary the energy of the beam, or does the beam energy have to be exactly matched with the geometry of the experiment, or how tunable is the frequency of the radiation?
So you see this. So this is about nuclear resonance, but this graph alone need not be nuclear resonance.
Right, but if you change the energy of the beam, the angles of reflection off the crystals will change, right?
The angle will change, right? But if you have this kind of configuration, you can change the angle. So you can put these two crystals in one table, and these two crystals are maybe separated by 20 meters or so. It's difficult to put in one table, right?
So you can rotate the crystals, or?
In principle, you can, as you change the Bragg angle, this path will change.
Right.
And so therefore you have to, these two crystals, you have to move in this way as long as well as you need to change angle. So you have to do this in concert.
I see.
So it's a sophisticated mechanical motion, but in principle, they
so how big? So how large is the range of wavelengths that you can generate with one device?
The fundamental limit of tunability with one set of the crystal is like 10%, and that limit is given by Bragg scattering bandwidth.
Right.
If you go off, then you go off this Bragg range. But the 10% you can do that.
You can do 10%. Wow.
Yeah.
Okay.
But 10% is but on the other hand, the bandwidth is a few milli electron volt. And 10% of 10 kilovolt is it's large. So,
right.
but
Yeah.
if you want to go to entirely other range, then you have to change the crystal.
Right.
Or you have to change this Bragg angle in large amount.
Mm-hmm.
So it's similar to a little bit similar to the undulator in the current light sources. You have a set of the undulators for different main range.
I see. I see.
Or sometimes they use a so-called carousel. You put,
Mm-hmm.
yeah.
Mm-hmm. Well, thanks again very much.
One question I had, Josh.
You can keep talking. I'm just going to stop my video and audio because I have to putter around here and tend to some other things. But I'll leave the session running, and then.
Okay.
Yeah.
Thank
you, Josh.
Thank you, Josh.
Also, Kristen, thank you for
Nice to meet you. Yeah.
Okay. Kristen, if you need to leave, that's also fine. We should have some more questions.
Yeah.
Mark,
So
go ahead.
it's at, yeah.